Hello, I'm Brian Larson. The last user day, I was still part of Kansas State University, but my funding through the Food and Drug Administration Scholar in Residence ran out. I still work with John Hatcliffe. We'll talk about that. Peter Filer had a great definition of assurance. I'm going to read that again. Sufficient evidence that a system implementation meets system requirements. We have lots of non-functional behaviors, but what I'm concerned about here is that it behaves, the function behaves correctly. And how do we know that the true behavior conforms to the what we want? Anita's gone, but a lot of times formal methods have been disappointing. They've been too difficult to use. And so having something that real engineers can use is crucial for actually getting them to be used. And that's what I have been trying to do. BLESS is the behavior language for embedded systems with software. It also has a verification tool that goes with it. And there's two parts of it that have a specification part, declarative specification of behavior, and then an implementation that you can show meets its specification. So you do AADL for the system structure. As mentioned, there's the Behavior Annex standard, which is very similar to it. BLESS you can think of as a superset of the BA behavior, which adds some other features. And then we also have this specification language, which is attached to AADL components. And a proof altogether ties the structure, behavior, and the specifications all together. Now, it's not theorem proving. Theorem proving is really hard. The BLESS proof assistant transforms programs with proof outlines. Some smart programmer has got to have stated, what is true about the system when I'm in a particular state. They also would say, if I sent an event out a port, what is true about the system, or if they're receiving one, what they would assume. And the proofs use the same language. You're not going to LTL or COC or some other kind of a thing. So the proofs are in the same language as you program with. Here is a little example of temporal logic. The temporal logic we found to work is a simple extension of first order predicates where we have a at sign that says evaluate the predicate on the left at the time on the right. And this is a predicate which is used for a pacemaker to say, when do I put out a pace? And this says that either I had a natural heartbeat or a paced heartbeat, one lower rate limited interval previously, like 1,000 milliseconds for 60 beats per minute lower rate. And I did not have one since then. Okay? So in the period between then and now, I have not had a heartbeat. So therefore, I need to put one out now. So if I'm going to put a pace, I had a pace or a sense 1 second ago, and nothing has happened in between. So we have a declarative specification of behavior. For components, we use the AADL property mechanism and attach what is true or assumed to various features. In this case, the P port has this VP predicate attached to it. Then we also have a state transition machine. It began as BLESS, where we would add assertions. That's what's true about the system at particular points. And then that would become part of precondition, postcondition type proof for actions that were done as part of transitions. Here's just a little bit of it. We got variables to hold state. This last says what that variable last beat means. It means that I either had a pace or a sense at this timestamp of last beat. And then a series of states, of which each one of those has a predicate or an assertion about what is true in those states. We then have transitions, which are very similar to what you have in BA, but there are interspersed within them some of these assertions about what would be true at particular points when I am doing an action. We have a text editor that's integrated with OSATE, and then a proof assistant will help with, given human guidance, transform the proof outline that has been included in the behavior into a complete deductive proof, where deductive proof is actually a sequence of theorems that are human readable, that are traceable back to the code they came from. So if you come to a point where you're trying to prove it correct and you get something that's obviously wrong, it's a false thing, you can't prove it, you can trace it back to where it came from in your code and fix it there, and then redo the proof statement. The last theorem says that all of the verification conditions have been met for all possible executions. You're still going to be doing testing, but to cover the entire state space, now you have a proof that the rest of the state space you were unable to test is also conformant to its specification. Composition is really important. You want to be able to put these things together and know they work together. If you can think of these predicates attached to ports as being an extra thing on top of types. So when we're going to do the virtual integration, we have not just that the types are correct, but this one is saying when I'm sending an event, I'm assuring that this is true. And on the other side, it says what I'm assuming to be true. And I can have assume guarantee proofs that will then show they're together. So this is one level up. Early on, doing your specification, you can then assure that you've got the virtual integration at a much deeper level before you've done any of the coding at all. We could do some code generation. We generate C++. This was with the isosceles platform that Tyler talked about, was demonstrated at the last meeting. We also have a language called Slang, which is a subset of Scala with John Hatcliffe will be talking some more about that this afternoon. They have an overall rubric where they can then make sure that the architecture and the relationships exchange information correctly with runtime services, and then incorporate the proved correct code from BLES for components. And we AADL plus BLES brings together the structure, specification, and behavior in coherent manner. Like other forms of engineering, it treats its subject as a mathematical object. Too often we'll do math on everything right to where we have the software, and then we program it and we run a few tests and hope that it works. The Food and Drug Administration would like to ask people who are submitting software-based medical devices, what is the fraction of your state space that you are able to test? And then how do you know that the rest of the state space is also safe and effective? Well, they don't ask this question because it would basically stop the medical device industry that uses computers. Because other than BLES, there's no way to have assurance over the whole state space. So we have proof of concept code, 2 different compilation chains. A little earlier effort, we generated the SCADE suite if you wanted to use the ANSYS tool. With Pierre, would like to incorporate BLES with AADL Inspector. There are a couple of videos. These were done by Kansas State, but they feature BLES greatly. So take a look at these. These slides will be available. And if you want to actually use it yourself, here's some instructions, but otherwise, We'll be out there. I will show an example of the infusion pump that was mentioned and was done in collaboration with Adventium and Kansas State. Any questions? Okay, thank you. Here.